All right, folks, as we are getting started here, and as you are coloring in this group of the post-transition metals, there's a few things I want to talk about. The first thing I want to talk about is you have a little bit of a choice in how you color this. Because there's a certain set of elements here that are colored in, but I will point out that beneath them, we have these four elements: nihonium, flerovium, moscovium, and livermorium. You have a choice to make with these four elements. You see, those four elements are probably post-transition metals, and so it would be a reasonable thing to do to color them in the same color that you do these guys. At the same time, it's important to acknowledge that these four elements, again, nihonium, flerovium, moscovium, and livermorium, those four elements are synthetic elements. They were made in a lab. They're really unstable. They immediately break down into other elements. And because they're so unstable and it's so hard to make it, we haven't really had the opportunity to really spend time studying them and seeing how they behave and being able to go, yeah, these do behave like the post-transition metals. What all this means is you have an option. You have two choices, depending on which thing will bother you more. If it will bother you more to have this idea of oh, well, I could color them in, but maybe someday we'll find out that we were actually wrong and they're not post-transition metals, and if the idea that there's the possibility, however slight, that you might be wrong is distressing to you, then you can leave them blank and not color them in at all. That is a valid option.
Have you left them blank?
I colored them in because I fall into the second category, which is to say I will be more annoyed by the incompleteness of my periodic table. So I colored those in. They probably are post-transition metals. And honestly, the stakes here are very low because one of the things about being synthetic elements that are really expensive to make and only last for a very brief period of time is that you're probably never actually going to use them in a chemistry lab. So it's really unlikely you're ever going to be asked any questions about these. So it's your choice whether you want to color these four in or not. If your preference is, I want it to be complete, I want it to be beautiful, go ahead and color them in, it's fine. If your preference is, I want to make sure that there is no chance that I ever write anything inaccurate down, then don't color them in. And both of these are perfectly fine and valid choices. All right, so that was the first disclaimer, which was about your choice to color in those four elements. The second disclaimer here. Look, scientists love to categorize things, and oftentimes things will be like, oh, they're in this category or they're in that category. What we're doing right now is fundamentally, we're looking at these elements and we're being like, oh, you're in this category. Can I ask y'all to not play that? The sound actually picks up on the film, and it's really obnoxious. So let's please not be doing that. All right, so anyway, I was saying, scientists love to categorize things. What we've been doing in this class is very much a work of putting things into categories. However, in nature, things are not as perfectly categorized as they're either this or that. It is not really the case that things are, either you're male or you're female. No, intersex people exist, right? It's also not the case that you are oh, either you are a metal or you're a non-metal, right? There is a group that forms the boundary between those that has some of the properties of each. And we call them metalloids, and it's kind of a squiffy group. The two groups we're going to talk about are the post-transition metals and the metalloids. And there is some mild disagreement about exactly which elements belong in which group. You will likely encounter periodic tables that have chosen slightly different sets of elements for where they draw the boundary between the post-transition metals and the metalloids. And that is okay, because it's not really a strict categorization. Really, it's, a spectrum of properties that range from the most metallic things or the stuff in that transition metals category. And then as we move to either side, we get a little bit less intense with our metal properties. All right, go ahead and sharpen your pencil. Yes, Yossi?
If it was discovered that the post-transition metals aren't actually post-transition metals, that group, would that be the same group that's classified differently? Like, would all those...
Oh, like these four?
Yeah.
Yeah, these four are either going to be post-transition metals.
Wait, which ones are post-transition metals?
So no, the ones in blue here, these are post-transition metals.
Okay.
The four right beneath them, nihonium, flerovium, moscovium, livermorium, those are probably post-transition metals. Somebody might later draw the properties and be like, oh, but are they really slightly differently? But you'll notice that like the post-transition metals kind of forms a shape like this. So it's more likely that these would be post-transition metals than that they would be anything else. Like the trend is one that suggests that we're likely to include them, which is why I colored them in. But
interesting.
It hasn't been officially proven yet, and so it's okay to leave them blank if you prefer to leave them blank. Some of you might take joy from knowing that there's things that we don't know about the periodic table, and that might be a source of joy for some of you. Yes, Raphael? Yes, you can go to the bathroom. All right. Now that we have had a chance to do our coloring, let's summarize what we're going to be learning today. Today, we're going to be talking about two separate groups. You've colored in one of these sets of groups, which is the post-transition metals. We are also going to color in the metalloids, and we're going to talk about things in group 3A, and what their charge is, or what their charges tend to be. So let's start by talking about, let's talk about aluminum. Aluminum is one of these post-transition metals. All right, so let's talk about aluminum. Aluminum is one of these post-transition metals. I'm not going to make you draw a planetary model of it today. That's on the class kick, so you'll have a chance to do that there. But I do want you to just sort of think it through. Raise your hand if you can tell me how many valence electrons is aluminum going to have. Let's go to Danny.
It's going to have 3 valence electrons.
3 valence electrons. Raise your hand if you can tell me when this forms an ion, how will it go about following the octet rule? Let's go to Yossi.
It will lose 3 electrons.
It will lose 3 electrons. Raise your hand if you can tell me when we lose 3 electrons, what does your charge become? Yeah, Carter. Positive 3, because we're subtracting those negatives. So subtracting those negatives does make us positive.
Removing cold cubes.
Positive. Thank you so much, Diane, for holding me accountable. Thank you, Lucas. So, aluminum is going to make things with a charge of +3. Above column 3A, on your periodic table, you can go ahead and fill in a +3 above column 3A. Now, we are not going to go and fill in. You'll notice a lot of these post-transition metals are also in column 4A. We are not going to fill in a charge above column 4A. Right? And there's a couple reasons. Some elements, like carbon, don't tend to form ions at all. They're kind of stuck in the middle. They're like, oh, well, will I lose or will I gain? And so they don't form anything. So some things don't form ions there. Others, like tin and lead, can be a little bit more complicated with what kind of ions they form, in part because they're like the transition metals in that way. So we are not going to fill in anything above, or any charge above column 4A. If you like, you could write an N/A for not applicable above column 4A, just to remind yourself that like carbon's not going to be forming ions. All right. So first things first, post-transition metals. Let's talk about what the name means. They are called the post-transition metals because the word post means after. So these are the metals that come after the transition metals on the periodic table.
So they're like the little siblings of the transition metals?
Yeah. And as we move farther to the right with our metals, we're going to find that the properties of metals get a little bit less intense. So I told you yesterday, like, hey, the transition metals, those are the most metally, the most stereotypical of all the metals. The post-transition metals, they still have all of our metal properties, which you've written down 1,000,000 times in our notes. We know they are malleable, ductile, conductive, and they form positive cations. But they are not as intense about these properties. In particular, they tend to have lower melting points compared to other metals. We good? All right. If you look at the set of elements you just colored in, you might see some familiar things there. For example, Sn, element number 50, that's tin. Who remembers when we used tin in our classroom? Lisa.
It melted very, very, very quickly and easily at a low point. Well, it would.
With
the
the
point that
soldering
tin would melt at would burn my hand.
Yes.
But
Right, but only a couple 100 degrees Celsius, right?
yeah.
Like, tin had a relatively low melting point. We were able to melt it with a soldering iron when we weren't able to melt the copper with a soldering iron. So that is one of the ways in which these post-transition metals are really stereotypical. They tend to have lower melting points than the transition metals. Yeah?
Is that why some solder is made out of lead?
Yes. So a lot of solder is also made out of lead. Same reason why it has a lower melting point, right? So tin is element number 50, Sn on your periodic table. Lead is element 82, Pb on your periodic table. Those are both post-transition metals, and they have this post-transition metal quality of having a lower melting point. Of the transition metals, the 3 transition metals that have the lowest melting points are mercury, zinc, and cadmium. And I want you to note, those are all the way to the right on the very edge of the transition metals. So as we move to the right with these post-transition metals, we're getting a little less intensive about our metal properties, particularly that low melting point. In fact, while you wouldn't want to play with mercury, because mercury is really toxic, there is another metal that has a similarly low melting point. This one is it becomes a liquid at 30 degrees Celsius, which is right around human body temperature. And it's gallium. I have here a vial of gallium, which I am going to let us play with. Now, before we play with the gallium, here's how it's going to work. First of all, you should be aware that gallium will leave a gray residue on your hands that can very quickly spread and get everywhere. So the first note I want to have about this is immediately after you handle the gallium, you need to go wash your hands, and you need to wash them with soap in order to remove that residue. Otherwise, there will be like a gray filmy residue that gets all over your tables and all over your iPad touchscreen. Okay?
No, there's a lot of stuff.
Yeah, so back here you can see there's that table has a lot of gallium residue on it. Somebody didn't wash their hands, right? So that's the first thing. Some things I want you to notice. Some things I want you to notice about the gallium. Fun fact about human skin, you actually don't have any chemical sensors for moisture. You can't actually feel wetness. What you can feel is the change in temperature that comes from evaporative cooling, which is a thing that happens when things are wet. But the gallium isn't going to evaporate, right? It's the temperature which it turns into a gas is really high, so you're not going to have any evaporation. So you'll be able to hold this thing in your hand that is very clearly a liquid, and it won't feel wet, right? Which is a very weird sensation, and I want you to notice it.
Try it.
Okay, soon. All right, folks, you can start coloring
Are you gonna start
in the
here?
metalloids, and I am going to start here to show you
Color
this.
is it? Are they green?
Yeah, green. All right. So Talia, you want to come here? Right, it's non-toxic. So make a cup with your hand. You're going to just gently pour it in. There you go.
Wait, that is weird.
So notice how it doesn't feel wet. We don't have that same sensation of wetness. Careful not to spill it. You can touch it if you like. It's really weird. It's got a lot of cohesion to it. Right? It's just this super weird thing. Right? And you'll notice it freezes on the back of your nail because it's not as warm as the rest of you.
Wait, yeah, that really feels like a solid, like you're gonna pop it or something.
Yeah, I know, bizarre, right? All right, pour it back into my hand slowly. And we'll take what's left there. and then go wash your hands. All right. Refocusing back to lecture time. It'll be real fast. The metalloids. So this group is neither metals, nor is it nonmetals. It's neither metals, nor is it nonmetals. They are in between these two groups in properties. So on your key, they shouldn't be listed as a metal, they shouldn't be listed as a nonmetal. They are neither. Now, these groups contain elements that are right on the boundary between what it is to be a metal and what it is to be a nonmetal. So they have some of the properties of each. For example, metals tend to be conductive. Nonmetals tend to be insulators. The metalloids are what we call semiconductors. They're neither metals nor are they nonmetals. They are in between the two. Go ahead. I appreciate all you waiting for the stitch in the conversation.
I said conductors, that was close enough.
All right. So, while our metals were malleable, the metalloids behave more like nonmetals. You remember that sort of thought experiment with the soda can, like the Coca-Cola can versus the Coca-Cola bottle? What's a glass bottle made of? Does anyone know?
Glass.
What's glass made of? Is it
Silicone.
Emily? It's silicone. Silicone is what glass is made of. And glass shatters when you hit it because it's brittle, right? Because it is so brittle, glass tends to shatter. So in that way, the metalloids are more like the nonmetals than they are like the metals. We've talked about these three different kinds of bonds and how like only metals can do metallic bonds, only nonmetals can do covalent bonds, and then a metal paired with a nonmetal can do an ionic bond. But these metalloids, some of them can do covalent bonds. Some of them can make alloys with metals and participate in a metallic bond. Some of them make ions and can do ionic bonding. So they're sort of in between in the properties when it comes to bonding. They can do a little bit of everything, depending on the element. And honestly, that's what I need you to know about the metalloids. Yossi, you've got a question?
Yeah, will you go back, like, will you at any point go back and tell us which ones are which?
Oh,
Which ones
you
are
should
the
be able to
metalloids?
see on this.
Okay, wait,
Yes.
is
Boron,
is astatine?
astatine is in the halogens.
Okay.
So it's tellurium, antimony, arsenic, germanium, silicon, and boron that are our metalloids. However, I will say, the boundaries between these groups are a little bit squiffy. And there, I think, are people who consider astatine a metalloid rather than a halogen. The boundaries are a little bit wonky. So remember, these things are not like, hey, it's this or it's that. It is a spectrum, right? So there's intermediary, like intermediate states that things can be in. The metalloids are a great example of an intermediate in that they are sort of like metals, sort of like nonmetals, a little bit of both. All right, folks. On that note, you can go back to your class kick. I've just given you the last couple answers that